Hello, folks. Today in this video, we're going to talk about measurement in physics. We're going to talk about different mathematical concepts and quantities that you're going to need to be able to take good measurements in a physics course. Let's get started. So our first topic that we're going to talk about today is the idea of significant figures. Now, significant figures comes up a lot when you're thinking about measurement. If you imagine something like a ruler, for example, let's say I've got a ruler and it's got marks on it, and let's say it's got a 1 centimeter here and then 2 centimeters here. It will obviously then have, graduations in between that 1 and the 2. Well, these tell you how precise your measurement can be. Anything you measure with is going to have a precision to it. So if you were to write down, the length of something that you measure with this ruler, you might write something like 1.2 or 1.25, but you wouldn't want to write down like 1.266754331, right? Because your ruler clearly cannot measure that precisely how long that object is. And so we represent how well we know a measured quantity using significant figures. Now, there are some rules with significant figures to be aware of. If you're taking a look at a number, let's say it's 0.00205.040. Let's figure out how many significant figures are in this. We can apply some easy rules. The first rule is that all non-zero digits are significant. So if you're looking and figuring out which one of these digits are significant, well, the 2, the 5, and the 4 definitely are because they are non-zero digits. Then we get to the zeros, which are always, of course, the part that's a little trickier. The first thing to know is that leading zeros are never significant. They're not going to be significant. What I mean by a leading zero is I mean the zeros in front of the numbers. So anything in front of the first non-zero number is never going to be significant. So those are not significant figures. Then we deal with trailing zeros, zeros that come after a number. Trailing zeros are only significant if they follow a decimal point, or if there is a decimal point in the number. So if you're looking here, I can see that this 0 is at the very end of our number, and there is a decimal point in my number, and so that 0 will be significant. And then there's kind of a corollary rule that I didn't put on here, but that if you have a 0 in between two significant numbers, it's also significant. It's a placeholder that tells you, to separate the 2 and the 5. So those would be significant as well. So this number would have 6 significant figures. Some other examples that can sometimes come up, you might have a case where you have 210. Well, using our rules, 210 will only have 2 sig figs because the 2 and the 1 are significant. This 0 is trailing, but there's no decimal point, so it is not significant. You can change this to have 3 significant figures by putting a dot or a decimal point after that. That indicates that the 0 actually is significant. So I said follow here, but really what I mean is if there's a decimal point present in the number, this one then has 3 significant figures. Okay, then our rules for significant figures. So you got multiplication and division, which is by far the one that comes up the most in most physics formulas. We're multiplying and dividing numbers. And the result here is very simple. The result should have the same number of significant digits as the factor with the least. So if you're taking two numbers, let's say you take 17.4 and you multiply that by 2.5. And so you get out your calculator first and you take 17.4. If I can pull a calculator out that actually is charged. This one works, perfect. 17.4 times 2.5, and I get 43.5 in my calculator. So 43.5 is my answer, but that might not have the correct number of significant figures. I always have to round this based on my rule here. My rule is that it should have the same number of significant digits as the factor with the least. Well, 17.4 has 3 sig figs. But 2.5 only has 2, meaning my answer should only have 2 significant figures. Because 43.5 has 3, I need to round that last digit up or down, depending on whether it's below or above 5. Since this is 5, I'll round it up. And so my answer for this one is going to be 44. Now that's the one that comes up the most, but you will see some of these other rules happen. Addition and subtraction can come up, and it's a little different than multiplication and division. The way that addition and subtraction works is you want to line up your numbers based on their places, like their tens place and the hundreds place, and your result is rounded to whatever the last common decimal place actually is. So if you take 100.4 and add it to 2.55. I can see I've lined everything up here that the last common place, the place that they both have, is the tenths place here. And so you can do your addition and subtraction like normal. I get 102.95. And then I'm going to want to round my number, though, to the tenths place because this hundredths place appears in this number, but not this one. So I'm going to round to the tenths place here. Now, I've given us a little bit of a hard one because if I round this 5 up, I get 10 here. So I got to put that over. So it's 103.0. That 0.0 is important because it keeps that tenths place. I don't want to drop the 0, even though it's a 0, because it is significant there as well. Notice that my answer has 4 sig figs, even though this one only has 3. This is not like multiplication and division. In addition and subtraction, you can make an answer that has more sig figs than the ones that it came into. It's a little hard to see, but this last part of the slide here, I can probably hide this, is that exact or defined quantities don't use sig figs. So if you were to do some stoichiometry like in chemistry, and you knew that there were 2 atoms of hydrogen in H2O, you wouldn't round your answer to 1 sig fig because there's the 2. Because that 2 H's in H2O is not a measurement. There are 2 H's in H2O. It's not like there's any uncertainty about how many H's are in an H2O molecule. So that's an exact number, and so that will not use significant figures. So that comes up a couple times, and we'll talk about that when it happens. Now there is one more kind of odd significant figure rule, and it's the significant figure rule that you deal with when you deal with logarithms and exponents. You want to be familiar with logs and exponents, and if you have any questions about those, come let me know. For logarithms, the rule is that the number of sig figs in the original number should match the number of digits after the decimal point in the answer. So let me kind of explain that a little bit slower. So you're going to take a look at your number that you're taking the log of. I'm going to look here at 1.040. And I will say that has 4 significant figures. What that means then is that whatever number I get in my calculator, it should have 4 digits after the decimal point. So I don't care about the before the decimal point stuff at all. I'm just looking at afterwards. So you would take log of 1.040 in your calculator, and I get 0.0170333339, a lot of digits. I'm going to round it to 4 places after the decimal, not 4 sig figs necessarily, 4 places after the decimal. So 0, 1, 7, 0, that's 4 places, and then I'm going to go ahead and stop there. So a bit of a weird rule, but that's the way it works. And another example I did was a log of 2.5. Here, since this is 2 sig figs, you're going to go 2 places after the decimal point. For this next one, it's the exact opposite. If you're doing exponentiation, if you're taking 10 to some number and e to some number, and by the way, those will be the only bases we really ever see in physics, log base 10 and log base e. So those will be the ones we're doing exponentiation with. The number of sig figs after the decimal place should match the number of sig figs in the answer. So it's just the exact opposite. Because 2.41 has 2 sig figs after the decimal point, my answer should have 2 sig figs. So if you take 10 to the 2.41 in your calculator, I get 257.039578.3. I get a lot of numbers. I'm going to round this because this has 2 after the decimal place to 2 sig figs. To get 2 sig figs, I got to round all the way to the tens place, 2 something, and then a 0. That's how I get my 260. So this next one, this has 3 after the decimal point, so I rounded it to 3 significant figures. Okay, that's it about sig figs. There's a couple more topics about measurement in physics to take a look at here, and they all deal with units and unit conversions. You do want to be able to do unit conversions between metric and English units or different types of metric units using powers of 10. I'm never going to make you memorize specific conversion factors, the 2.54 centimeters per inch or anything like that. All I want you to be able to know and memorize is your basic powers of 10. So pico, nano, micro, milli, deci, base, kilo, all of those. Do know this list, but other than that, I will always give you the conversion factor that you'll need. Now, what method you use for doing unit conversions does not matter to me at all. I am a big fan, and I'll show you here, of doing dimensional analysis because it allows you to chain multiple steps together, which is super nice. For example, if I wanted to convert 3.6 kilometers to, let's say, inches, It's a big number, but we'll see how many inches are in 3.6 kilometers. Well, I need to do some conversions. I'm first going to remember that 1 kilometer is 10 to the third meters, or 1,000 meters, and get back to my base unit. Then I need to go to centimeters, because I know there's how many centimeters in an inch. And so I remember that 1 meter is 100 centimeters. I could have done that all in one step. If you can remember and know how to do like the jumps between kilo and centi and things like that, and if you do, that's great. I just wanted to show that as a multi-step thing, and that's the great thing about dimensional analysis, right? Is that you can do multiple steps and chain them all up. And then now I have my centimeters to an inch. I'm going to put the centimeters in the bottom, and the reason I need to do that is I want to cancel out these units, so I'm left with inches at the top, and I get 1 inch there. Inch, not im. And then I'll go ahead and do that in my calculator. 3.6 times 10 to the fifth, and then divided by 2.4, which is quite a big number. I get 1.4 times 10 to the 3.45, and that's in inches. Now, you'll notice I did mine in instead notation. You do not need to, but I did it because it helps me with the sig figs. That way, I know it's supposed to be two significant figures because 2 went in, and then this one was 3, and these are exacts, so I know my answer should be 2 there. But you're welcome to not use sign of notation if you don't want. Now, there is one type of unit conversion that sometimes trips people up, and that would be, what if I was trying to take a number like 36 square centimeters and convert that to square inches? How do I deal with this square? Because typically my unit conversions are not in terms of squares, they're in terms of the base numbers. Well, there's an easy way to deal with that with dimensional analysis. Take your 36 centimeters squared and do your unit conversion like you normally would, 2.54 centimeters to 1 inch. And if you think about this in terms of units, this would only cancel out one of my centimeters, not both of them. So you might see where I'm going here. You need 2 of these unit conversions. You could write them both side to side, or I find it easy, just imagine squaring that. So just put a square there, and that tells me, yeah, I'm going to square this conversion factor, and that's going to take care of my units and get me to square inches. So it'd be 36 divided by 2.54 squared, and I end up getting 5.6 square inches. Okay, last thing to talk about here is combined units or derived units. What do I mean by this? We typically in physics are going to deal with units that are in some combination of base units. So, for example, we measure distances typically in meters, we measure time in seconds, and we measure mass in kilograms. So those are our base units. But let's say we're dealing with a unit that is combined. Let's say I want to find speed or velocity. Well, speed is distance divided by time. So our equations help me know what the unit's going to be for speed. It would simply be distance, which is meters, divided by second. So speed must have units of meters per second. And these can get quite complicated. Acceleration is meters per second squared, and they can get further and further. In fact, let's take a look at another formula, F equals m times a. So this is Newton's second law, and we can use units to help us kind of understand what the unit of force should actually be. You might remember that the unit of force is actually a Newton, named after Newton who made this law, but what is a Newton? What is that in terms of base units? How does that make sense? Well, we can use this equation to help us out. See, mass we know is measured in kilograms, and I just said that acceleration is measured in meters per second squared. So it must be true then that a Newton is a kilogram meter per second squared. So that's what we mean by combining units and writing them together. And we can always use formulas to help us do that. Okay, folks, thank you guys so much for watching. Have a fantastic rest of your day.